Hi, my name is Leonard, and I'll be talking about the invariance of the restricted Lie algebra structure of Hochschild cohomology. So this is joint work with Benjamin Briggs, who is also giving a talk at this conference. So if you're interested in this topic, and if you want to learn some applications about some of the results that I'll be presenting now, you should definitely check also his talk. So let me start with some notation. So for me, A will be a finite dimensional K algebra over an algebraically closed field K. And I'll denote by A superscript EV, the enveloping algebra of A, and by HH star of A, the Hochschild cohomology of A. This is just the X algebra of A as a AA bimodule with coefficients in itself. And in particular, if we are looking at the Hochschild cohomology of degree 1, this has a very intuitive description in terms of derivations of A, quotient the inner derivations, where the derivations of A are just k-linear maps that satisfy the Leibniz rule, whilst the inner derivations are derivations that are given by the additive commutator. And well, actually HH1 has a structure of a Lie algebra, and the Lie bracket is also very simple to define. So if I give you two derivations f and g, then the bracket between f and g is given by f composed with g minus g composed with f. And actually there has been recently a lot of interest in these Lie algebras. So there is work of Benson, Kessler, and Linkelmann. There is work of Linkelmann and myself. There is also work of Scholl, Solotar, and myself. There is work of Chaparro, Scholl, and Solotar, and there is also recent work of Eisele and Radschelders. And one of the reasons why people are interested in these Lie algebras is because they are invariant under various equivalencies. But on the other hand, usually it's very hard to compute these Lie algebras. But let me start with an easy example. So if we work over a field of positive characteristic, and if we denote by A just k of x over x to the p, then if we want to study HH1 of A, it's enough to study the derivations of A, because A is a commutative algebra, and these derivations has k bases given by f0 up to fp minus 1, where fi of x is equal to x to the I, for I that goes from 0 to p minus 1. And the reason why it's enough to define these derivations over x is because then we can apply the Leibniz rule. And as a Lie algebra, what we obtain is a Witt algebra. So it's a modular, simple Lie algebra. And well, as I said, HH1 is an invariant under various equivalencies, and the equivalents that we are interested in now were introduced by Brouet. So if we have two finite dimensional K algebras A and B, and we have two bimodules M and N, then we say that M and N induce a stable equivalence of Morita type between A and B if M and N are projective left and right modules, and if there is a bimodule isomorphism between M tensor with N and A plus a projective AA bimodule P. So the tensor product in this case is over B. And also if we have an isomorphism as BB bimodules between N tensor with M and B plus a projective BB bimodule Q. And well, we can think about stable equivalencies of Morita type as Morita equivalencies in the stable module category. And in particular, if we are dealing with self-injective algebras, then the stable module category is a triangulated category, and the functors that are given by tensoring with these two bimodules induce an equivalence of triangulated categories. And well, it turns out there is even much more structure on Hochschild cohomology. So Hochschild cohomology is a Gerstenhaber algebra. So this means there is a graded commutative algebra with respect to the cup product, is a graded Lie algebra of degree -1. And there is also a compatibility condition between these two structures, which is called Poisson identity. And well, an important theorem is partially due to Xi and partially to Koenig, Liu, and Zhou, which says that if we have two symmetric algebras A and B, which are stably equivalent of Morita type, then we have an isomorphism as Gerstenhaber algebras between the positive part of the Hochschild cohomology of A and the positive part of the Hochschild cohomology of B. So in particular, we have an isomorphism of Lie algebras between HH1 of A and HH1 of B. And it turns out that if we are working over a field of positive characteristic, we have even further structure. So in fact, this leads us to the notion of a restricted Lie algebra. So a Lie algebra is restricted if there exists a p-power map or p operator, which is just a map that goes from the Lie algebra to itself, which is compatible with the adjoint representation, addition, and scalar multiplication. So this is roughly the definition. I don't have, unfortunately, the time to give you all the details, but this is roughly the idea. And well, also in this context, there is a very important notion, which is the notion of a torus, which is just a restricted Lie subalgebra, which is abelian and which is generated by the so-called p idempotent elements, so are elements such that x to the p is equal to x. And why we are giving this definition is because HH1 is actually a restricted Lie algebra, and in order to define the p power map is very simple to define the p power map. So if we have a derivation f, then f to the p is just defined to be just as f composed with itself p times. And more generally, we have that actually the whole positive part of Hochschild cohomology is a graded restricted Lie algebra, although in this case, it's a bit harder to define the p power map. And well, but in this context, a natural question arises. So this was asked by Linkelmann. So, and is the following: is the restricted graded Lie algebra structure preserved under stable equivalence of Morita type for self-injective algebras? And well, the answer is yes for a subclass of HH1 called integrable derivations, but just last year we managed to work to prove in joint work with Benjamin Briggs that if we have two finite dimensional K algebras that are self-injective, and of course we are working with a field of positive characteristic, and if A and B are stably equivalent, there is a stable equivalence of Morita type between A and B, then we have an isomorphism as a restricted graded Lie algebras between the positive part of the Hochschild cohomology of A and the positive part of the Hochschild cohomology of B. And well, from this theorem, we can also extract more information. So for example, we have an isomorphism as Lie algebra, as restricted Lie algebras between the HH1 of A and HH1 of B. And also we obtain further invariant, and an invariant that will be important in Benstock is the maximal dimension of a p-toral subalgebra. So, well, I think this is a good place to stop. So thank you very much for your attention.